So today in AC electrical circuits we're going to be looking at lab number 5, capacitive reactance, and the objective. Capacitive reactance will be examined in this exercise. In particular, its relationship to capacitance and frequency will be investigating. And we're going to do a plot of capacitive reactance versus frequency. As always, I've given you some reference sections to read up on, and these are in Sham's Outlines Basic Electricity 2nd edition. So we're going to look at Chapter 14, Capacitance and Capacitance Reactance, and you may need to review Chapter 12, Principles of Alternating Current. So Chapter 14 starts off talking about the capacitor. Talks about the types of capacitors that we might encounter, talks about capacitors in series and parallel and how to add them together, talks about capacitive reactance and gives you the formula for Xc equals 1 over 2 pi Fc, talks about capacitive circuits, capacitance only, and RC in series, shows us the waveforms and the phasor diagrams for capacitance, and has a section on R and XC in series, which is what our lab is about today. Nice section on impedance in series RC circuits, and a nice example of a RC series circuit and the phasor diagrams that go with it. So in the theory overview, it says the current voltage characteristics of a capacitor is unlike that of typical resistors. While resistors show a constant resistance value over a wide range of frequencies, the equivalent ohmic value for a capacitor, known as capacitive reactance, is inversely proportional to the frequency. The capacitive reactance may be computed via the formula. So we can see that Xc, or capacitive reactance, is equal to minus J, indicating that it's minus 90 degrees, and it says inversely proportional, so it's 1 over 2 pi Fc, where F is the frequency. So you can see that the capacitive reactance changes inversely to the frequency. It goes on to say that the magnitude of capacitive reactance may be determined experimentally by feeding a capacitor a known current, measuring the resulting voltage and dividing the two, following Ohm's law. This process may be repeated across a range of frequencies in order to obtain a plot of capacitive reactance versus frequency. And it says an AC current source may be approximated by placing a large resistance in series with an AC voltage, the resistance being considerably larger than that of the maximum reactance expected. Today's equipment, we're going to be using the function generator, which is the circuit test SWF 7000. And the Tektronix oscilloscope, either the TDS 210 or the 1002, and our DMM, which will be the Mastec MSM 9803. We're going to be using a 10K ohm resistor, and I've given you a little graphic and the color codes for it. And we're going to use a 1 microfarad and a 2.2 microfarad capacitor. So these are my components for today. This is the 10K ohm resistor. Over here I have a electrolytic capacitor, and it's 1 microfarad, and you notice one leg is longer than the other. So it has a positive leg, so you have to put these ones in the right way around. The capacitor beside it is labeled 105. So that's 10 with 5 zeros after it, picofarads. So that ends up being 1 microfarad. So both of these are 1 microfarad. It's just the one in the can. Has to have a positive leg, so it has to go in the right way around. Over here I have the 2.2 microfarad capacitor, and it has a long leg. so it has to go in the right way around. And over here I have another little capacitor, and it's labeled 225. So that's 22 with 5 zeros after it, picofarads. So this ends up being our 2.2 microfarad capacitor. Now when you're using capacitors in AC circuits, you should really use the non-polarized capacitors. So we shouldn't use the one in the can. So these are my components that I'm going to be using today. So using the ohm meter, you can see my 10k ohm resistor is actually 10.01 k ohms. To measure capacitance, the red lead goes in the hole with a little capacitor symbol, the black lead goes into the common hole, and the knob on the digital multimeter goes all the way around till it points to this little capacitor symbol. Make sure that you use alligator clips and do not touch the metal parts of your alligator clips because it will affect the amount of capacitance. Now you might have to wait for the meter to stop working on the capacitor, but you can see my capacitor reads at 1.008 microfarads. And my 2.2 microfarad capacitor reads as 2.262 microfarads. So under equipment, I've recorded the model numbers of the pieces of equipment that I'm going to be using. I've X'd out the serial numbers because they're too hard to find. I've written down the measurements of my 10k ohm resistor, my 1 microfarad, and my 2.2 microfarad capacitor. And remember that the tolerance on the resistor is about plus or minus 5%, whereas the tolerance on capacitors can be 10% or greater. We have a simple series circuit schematic, and that is the symbol for our function generator. One resistor, one capacitor that connects back to the common on the function generator. So under procedure, the first thing we're going to do is create a current source. So using figure 5.1 with V in as 10 volts peak to peak and R of 10K, we're going to assume that the reactance of the capacitor is much smaller than 10K and can be ignored. So we want to determine the circulating current using measured component values and record in table 5.1. So all we're going to be doing on our circuit is putting in our 10K resistor. This guy will be 10 volts peak to peak, and we'll assume that this is going to be a short circuit or very, very low resistance. So then V equals IR, so I equals V over R. So using figure 5.1, we're going to set our power supply to 10 volts peak to peak. We're going to have a 10k ohm resistor, and we're going to assume that this capacitive reactance is going to be close to 0. So V equals IR. I will be equal to V over R. So that's equal to 10 volts peak to peak divided by 10k ohms. So we're looking at 1 milliamp peak to peak circulating in our circuit, assuming XC is very, very small. So in table 5.1, I've recorded 1 milliamp peak to peak. So under procedure, step 2, it's all about measuring reactance. We're going to build the circuit of figure 5.1. We're going to use the 10k ohm resistor and the 1 microfarad capacitor. We're going to place one probe across the generator and another across the capacitor. So we'll be looking at VC. We're going to start with our generator at 200 Hertz sine wave and 10 volts peak to peak. We're going to put the bandwidth limit on for both channels. So this is how I've set up my trainer. You can see the red line, which is the power line coming in from the function generator, goes to the top of my 10k ohm resistor. The 10k ohm resistor meets up with the leg on my capacitor, and this is a 1 microfarad capacitor, so it's labeled 105. Then the black lead comes out, and that goes back to the common of the function generator. Now I have the yellow lead going to the junction of the resistor and the capacitor, so that's so I can read the voltage across the capacitor. versus the total input voltage coming into my circuit. So I just wanted to show you the setup of the leads here. Notice all the black leads stacked together, and they go to the bottom of my capacitor, which was the black wire. I have my channel 2 for my oscilloscope going to the yellow terminal, which went to the midpoint between the resistor and the capacitor. I have the input from my function generator and channel 1 of the oscilloscope going to the red wire that went to the top of my resistor. My function generator, I have the power button pressed in. I have the sine wave button pressed in. I'm on the times 100 range. My OSC button is in the out position. All of my individual knobs are pushed in. And this last knob is turned fully counterclockwise. My main dial has dialed in 200, and the bottom indicator light is on where it says Hertz. So I'm looking at 200 Hertz. My amplitude knob has to be set from the oscilloscope screen. So this is my oscilloscope screen. I've done a factory reset and an auto set on it, and I'm just going to check channel 1 by pressing its menu button. You can see the coupling is on DC. I'm going to put it on AC. My bandwidth limit is off, so I want to turn that on. My volts per division is coarse, my probe is times 1, and my invert is off. I'm going to go to the channel 2 menu. I need my coupling to be on AC. I need my bandwidth limit to be on. Volts per division is coarse. My probe needs to be on times 1. And the invert is off. I've pressed my measure button, and I've set it up so that channel 1 displays frequency, channel 1 displays peak-to-peak voltage, and channel 2 displays peak-to-peak voltage. I haven't bothered with the other readings. You'll notice channel 1 is on 5 volts per division with bandwidth limit on. Channel 2 is 500 millivolts per division with bandwidth limit on. And my seconds per division is set to 1 millisecond per division. So, under procedure, step 3, I'm going to calculate the theoretical value of XC using the measured capacitor value and record this in table 5.2. So in table 5.2, we have to remember the formula for XC is equal to 1 over 2 pi FC. So the calculation is 1 divided by 2 times pi times 200 times, in my case, it was 1.008 microfarads. So that's times 10 to the power of minus 6. So if you're going to do 1 divided by, remember to put all of these in brackets. And the answer should be 789.46 ohms. So in step 4 of the procedure, we're going to record the peak-to-peak capacitor voltage in table 5.2. So from the screen I can see channel 2 peak-to-peak is 900 millivolts. So under procedure, step 5, using the source current from table 5.1 and the measured capacitor voltage, determine the experimental reactance and record it in table 5.2. Also compute and record the deviation. So in table 5.2, I've recorded 900 millivolts. And to calculate XC experimental, we have to remember that V equals IR. R is equal to V divided by I. So in our case, we take the 900 millivolts and divide it by the 1 milliamps from table 5.1, resulting in 900 ohms. So you can see XC, in theory, should have been somewhere around 790 ohms, An XC experimental turned out to be 900 ohms. I'll explain this discrepancy later on in the video. So under step 6 of the procedure, we're going to repeat steps 3 through 5 for the remaining frequencies of table 5.2. So in table 5.2, we're going to go from 200, 400, 600, 800, 1000, 1.2K, 1.6K, and 2K. So at 400 Hertz, channel 2 is at 460 millivolts. So at 600 Hertz, you can see the voltage across the capacitor is 308 millivolts. Please notice I've changed the volts per division for channel 2 and the seconds per division for my horizontal scale. So at 800 Hertz, the voltage across the capacitor is 232 millivolts. So at 1 kilohertz, the voltage across the capacitor is 192 millivolts. At 1.2 kilohertz, the voltage across the capacitor is 160 millivolts. At 1.6 kilohertz, the voltage across the capacitor is 120 millivolts. At 2 kilohertz, the voltage across my capacitor is 100 millivolts. So I've recorded my results in table 5.2, and I'll come back later and do the calculations for theory, XC experimental, and percent deviation. So in step 7 of the procedure, we're going to replace the 1 microfarad capacitor with the 2.2 microfarad unit and repeat steps 2 through 6, recording the results in table 5.3. I've replaced the 1 microfarad capacitor with the 2.2 microfarad capacitor that's labeled 225 on the package. So back at 200 Hertz, I have channel 1 at 5 volts per division, channel 2 at 100 millivolts per division, and my seconds per division set to 2.5 milliseconds. The voltage across my capacitor is 364 millivolts. At 400 Hertz, the voltage across my capacitor is 192 millivolts. At 600 Hertz, the voltage across my capacitor is 128 millivolts. At 800 Hertz, the voltage across my capacitor is 98 millivolts. At 1 kilohertz, the voltage across my capacitor is 80 millivolts. At 1.2 kilohertz, the voltage across my capacitor is 66.4 millivolts. At 1.6 kilohertz, the voltage across my capacitor is 50.4 millivolts. At 2 kilohertz, the voltage across my capacitor is 41.6 millivolts. Under VC peak-to-peak experimental, I've recorded all my readings. I'll come back later and calculate XC theory, XC experimental, and percent deviation. So I wanted to show you my results for table 5.3. This is with the capacitor at 2.2 microfarads. I've taken all my voltage readings across the capacitor, and you can see as the frequency increased, the amount of voltage drop on the capacitor decreased. So that was the trend we were looking for. I've gone in and calculated XC theory and XC experimental, and you can see we started somewhere around 350 to 360 ohms, generating a percent deviation of 3.5%. But as I increased my frequency, you can see the percent deviation increased until it was 19.4%. But the trend was correct, so I'm not too worried about these results. These are my results for table 5.2, and this was with the capacitor equal to 1 microfarad. I've taken all my voltage readings across the capacitor, and as I increased my frequency, you can see the voltage drop across the capacitor decreased. So this was the trend I was looking for. So as the frequency increased, XC decreased. So that was the trend I was looking for. But you'll notice in this case, I calculated 790 ohms, and I'm getting 900 ohms for a 14% deviation. And as I increase the frequency, my deviation increased to nearly 27%. So what has caused this? You have to remember that capacitance, or a capacitor, is made up of two plates separated by some kind of insulator. So in our case, when we build a circuit on a trainer and we push a wire into a connector, the wires have actually oxidized or started to rust. So as the connectors. Our connectors are fairly old. Those trainers are like 30, 40 years old, so their connections have oxidized a bit. So whenever you put a wire into a trainer, there's always a little bit of capacitance between the connection. Now you have to remember that in a series circuit, when we add a little bit of capacitance, what happens is the formula is 1 over Ct is equal to 1 over C1 plus 1 over C2. So just like resistors in parallel, capacitors in series decrease the amount of capacitance. So for our 1 microfarad capacitor, we had 900 ohms on XC. When we increased our capacitance to 2.2 microfarads, you can see the resistance of XC actually decreased. So when we add capacitors in series, the capacitance decreases. So the extra capacitance added to our circuit from just the connections we used on the breadboard decreased the amount of capacitance and actually increased the amount of XC that we're seeing in our results. So the increase from 800 ohms to 900 ohms was actually caused by the extra capacitance of wiring our circuit together using the old trainers and wires pressed into the breadboards. In step 8 of the procedure, we're going to be using the data of tables 5.2 and 5.3 to create plots of capacitive reactance versus frequency. So to plot capacitive reactance versus frequency, I'm going to use my graph paper in the portrait mode. The horizontal axes will be frequency in hertz, and I have to go from 0 to 2 kilohertz. So I'm going to do it in 200 hertz increments. And that should get me to 2 kilohertz before the end of the graph paper. XC, or capacitive reactance, is measured in ohms, and I'm going to plot that on the vertical scale. And looking at my data, I need to go from 0 ohms up to approximately 900 ohms. So on my graph paper, every 2 divisions will be 100 ohms, so 50 ohms per division. 150, 200, 250, 300, and so on, all the way up to 900 ohms. When plotting your points, remember that the formula is XC is equal to 1 over 2 pi FC, so this is not going to be a linear relationship. It's going to be some kind of curve. So when plotting my points, I realized that this was not going to be a linear or straight line, so you kind of have to sketch it in as you go along in parts and try and get a nice curve to it. So you can see this is my line for C equal 1 microfarad, and the whole curve shifts over for C equals 2.2 microfarads. And once again, you kind of have to sketch the line in as you go along, trying to get a nice curve out of it. So this is what your finished graph should look like. As always, we have questions to answer at the end of the lab. Today we have 5 questions. I'll leave those for you to answer. When you've completed your lab, show it to your instructor so they can initial it to indicate that it is complete.